Let me just check to make sure everything's up and running real quick, and then we can begin. Like we're doing good. Very good. Hopefully I keep up with chat. Sometimes it's harder for me to keep up chat. So today we're going to go over a not well-known feature of Xilinx called Xilinx Virtual Cable. This allows you to create your own network-based JTAG receiver. And we're going to show you a trick that I've done before on this channel. We did this with PCIe, where we did a Xilinx virtual cable to a PCIe memory map to convert that to JTAG signals and send that to the Microblaze Debug Module. That was for a Series 7 Artix FPGA. With the UltraScale and UltraScale Plus, there's a unique feature called JTAG, which gives you an internal JTAG port. So the idea is that we're going to connect our virtual cable directly to the internal JTAG through the USB-C data connection. And then we're going to be able to do Microblaze debugging. We're going to be able to use the internal logic analyzers, and we'll be able to use the BBRAM and eFuses. I would avoid eFusing. If you don't know what you're doing, you will brick your FPGA. So, okay, let's go look at the agenda real quick. I may move my face later. Okay, so we're going to look at how to do a simple bit file using their OK host, or their Opal Kelly USB host software. I actually found an error in their VHDL, so we'll have to make a little note to send that to Opal Kelly technical information, or technical support. Then we're going to show you, we're going to create, I already kind of started, create a simple Python file to get a dummy Xilinx virtual cable going. There shouldn't be an R there, it should be Xilinx virtual cable. Virtual cable Python file. And then we're going to connect it to the OK host API. And then we'll see how that goes. And then once we have that, we'll start working on some custom HDL wrapper to, with their USB host interface to connect to the JTAG interface. We may not be able to finish that tonight, but we'll see how far we can get. So first, let's talk about creating a simple bit file. So I've kind of already done it, and the synthesis worked out fine. But let's go through, let's start again so we can walk through this together. So let's open another one. We'll call this Xilinx Virtual Cable 001. They did do an update for the board files, so if you have the board files, maybe good to uninstall them and reinstall them. I'm not worrying about any of the board features, so we'll just click that so I have a easy access to the system, or easy access to the board. So what we're going to do now is we're going to add the constraint file, and we're just going to straight up copy the constraint file that they provided. Do I have it in my quick access? Okay. Samples. We're gonna use the counter sample for the XEM8. My eye is not finding it. Right there. I am a VHDL person. I'm sorry for everyone who's watching this who hates VHDL. All my examples are going to be in VHDL because that's what I do most of the day. So it's going to be easier for me. Verilog should be just as easy to follow. So now let's add the directory. They're expecting the work directory, which isn't the default directory when you do Xilinx. So let's talk about how we do this. We want this. So we're going to go to Opal Kelly from panel USB, from panel HDL, A320 AU25, sure. But we go here, right? We want to make sure we select work. It may work in the default lib. Actually, let's see if it works in the default lib, right? Let's remove that real quick and re-add it. I just want to see if the default lib works. If not, we can change it. I can show you how to change it to the work directory. Okay, sorry. Got a scratch in my throat. So let's go back to the VHDL. I'm just gonna grab the VHDL top real quick. We're gonna copy and change some names. So let's add a new VHDL file. Create file VHDL. Oh, we'll fix that in a second. We're gonna call this OK JTAG. OK JTAG.vhd. Okay, let's finish this. Yeah, I don't really care about that. We're gonna change this to VHDL. VHDL is the target language. So what we're gonna do now, go find where OK JTAG ended up. Okay, OK JTAG. I don't know why it's taking so long to open. We're gonna remove all this, do this, and I give you guys. I have to zoom in. I'm not used to having this type of setup. It looks like I grabbed it just fine, so I guess we don't have to change the library. Okay, that's good. So this, I'm not sure why it's unhappy about that. That's located in this component one, so that it should grab that. But let's go ahead back to the hierarchy here. Why is that? Make OK JTAG our set as top. And we're gonna see an error real quick. We'll fix it and rebuild. Okay, see all these hidden files? This is fun. This is fun. All these hidden files. So okay, let's go open the files real quick. Design Verilog. Yeah, so these files. Sure, we'll open it in the directory. Let's grab one of these. The register bridge, because I want to figure out how this works someday. But if we look at this, Opal Kelly is using Verilog type encryption that is done with Xilinx, and this is useful to protect your stuff. But there's one dislike I have of this. I can't do a Netlist analysis for anything with encryption like this in here. So if I try to go to I'll show you in a second. If I try to look at the netlist, we'll see what happens, right? We'll see if it has that issue. If we're gonna have that issue, that's gonna make me hard time to debug. So I'm gonna have to put in like a parameter to enable or disable this feature so I can look at the netlist. But yeah, let me show you. Let's walk through this. It's easier to show you. So if we run synthesis, it's going to yell at me. And I'm going to need to record that issue. We're going to do Opal Kelly XEM8320 issues to report. Okay. While that's running, let's go and talk about this transceiver port. So yeah, Xilinx has a feature where it's called the Xilinx virtual cable. And what it basically does, I've worked through this before, so if you ever want to see it working, I have it on GitHub under BYU, CCL, Fiat. Maybe we can post this link. How about we just put that link into chat? Sign in real quick. Oopsies. No, watchy. Here's the link, the chat. People can click it. Okay. So that's the transceiver port. So I'm going to take this file right here. I'm going to copy and paste it to a local Python file and show you how it works. We'll walk through it on that file. Okay, so we have this message. We're going to copy this message so I can report it. And we're going to go to that line real quick. It's line 82. Oh, of okay host, right? Takes a while now. Used to be this bad. 80. Oh, that's the Verilog one. Sorry. Libraries. VHDL, please. To do. I should probably do this with a better IDE. Okay, so we're gonna copy this line. Yeah, just copy it again. 0.0. 0. Okay. So saving it. Now let's rerun synthesis and let's see, synthesis. I doubt synthesis is going to take long at all. These are all our encrypted registers that we know nothing about. So I want to see if Vivado gives me the option to look at the netlist. So we're going to open the synthesized design and see if we can look at the netlist. And we'll post this project on GitHub later. And so people can see how to do this. So, like if I do F4, okay, right. What if I do this guy? Okay, it looks like we still can look at the netlist. I'm not sure how much Opal Kelly appreciates this, but we still can view the netlist, so that's good. We can't. So if I try to say export this, so let's export this hardware. Not export hardware. If we export the netlist, and I want to export it as a Verilog file, right? It should prevent me. Okay, this should prevent me from temp.v, right? So it worked. Shall we see what that ended up being? XEM A25 temp. If I edit this, there should be encrypted stuff in here, shouldn't there? It's all primitives. There we go. Here we go. So this is where they have the protected modules. Whee! So you still can view the netlist, you still can export what you can, and that seems good. I like that. But there may be times where I need to. What's the netlist look like? Let's. I'm going to export the netlist real quick. I do netlist edif manipulation for TMR at BYU. We do edif. Let's see what this turns out to be. I'm just curious because how do we handle encrypted cores in an edif? I didn't see anything encrypted per se. So I'm not sure what this level of encryption does. We potentially can look at the netlist. I mean, you have the netlist, you have the design potentially. I mean, it's not going to be easy to rebuild per se, but it's something to think about. Okay. I think this is good. We're doing good so far. Okay, let's go ahead. We don't need to generate this now. I just wanted to show you how to set it up. Fairly easy. So let's go back to our virtual cable that we're playing around with. So if we head here, we have a file. So if we open this. Okay, so what this file does, we have a server. These registers are based upon Xilinx's JTAG IP core. Or, what's it, AXI to JTAG IP core. So these aren't really relevant right now, along with this. But this is the IP address and the port. Do I have it running right now? Okay, we have the keyboard interrupt. And so when this boots up, so we start a server and we do some Python multiprocessing. We start the server. And then we create a TCP port with a specific port filler, but we want fast response. That's just kind of the command. So we do this. Let's print this command, and this is the command you would run. And mine's just going to automatically hook up because I already have it listening. And then we have certain commands that we are grabbing from the package. So we're going to look at the first few 2 bytes, 3 bytes, yeah, 2 bytes, yeah, 2 bytes. This is general information. This send data, transmitted data. Oh, we're sending back the data. Interesting. I'm not sure exactly what this is doing, but it looks like we're just responding. And this is where we handle the JTAG connections here. So we grab different information from here. I kind of already parsed this out with the other one, so it just kind of works right now, so it's really nice. But we will print out the length, the TMS, the TDI, and then we want to grab the TDI, which I've hard coded to 0 to this moment. The bytes, and if we have less than 4 bytes in a transaction, we have it set up so we do a smaller transaction. Okay, so let me show you how this works. Let's go ahead and kill the hardware server. Let's go to details, make sure we don't have a hardware server up and running. Looks like we don't have a hardware server going up. Okay, cool. So we're gonna run this over here. Let me make sure you guys can actually see this. There we go. Right. All the way. Yeah, we can do it. Okay. Now we're gonna open up the Vivado tickle shell. Bring that over here. Oh, there we go. Yeah. Oh, stop that. So, are we already transferring, or is this okay? Now we're gonna do XSDB. And we see the command there, connect. So we're just going to type that command here, xvc.url 127.0.0.1, which is your local host, and then we're going to do 4000. And as soon as this connects, we'll see we got info, and now it's trying to communicate. And if we go JTAG targets right here, we now have a Xilinx virtual cable, air, shift through all zeros. Okay, good. Which one we want to do? I think we want to, not instead of counters, we would want to do first one. Let's go look at the first example real quick. I think that's the one we want to do. Samples first. 83020 VHDL. Notepad++. LEDs is the 0 wire, so we can just send things to 0. Okay, it sounds good. So we're always sending zeros, right? Yes. I'm kind of confused why TDI is greater than. TDI should be 32 bits. Yeah, 32 bits. Okay, so it doesn't look like we're doing that much interesting stuff here. What should we do? Maybe we'll just have a counter. We'll just set up oh. What's this say? Oh. That was weird. We'll have to figure out that later. Okay, so yeah, let's go ahead and do that. So let's bring up our Python example for the desk tester and kind of copy how they did things. So we're gonna need to import OK, maybe string, but we'll figure that out. I wonder if we're just spamming that. Okay, so before we start the server now, what we're going to do is set key, reset, crypt, decrypt. Okay. So yeah, let's go ahead and we're just gonna copy and paste that right here. It looks like it worked well, and we're gonna do first. I'll go back over here. There we go. And let's go and debug off for now. Yeah, I'll keep that for now. So if we do this, oh, it's just a function. So what we're gonna do is just do a return here. Return, 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 return. We're not gonna worry about that at all. Oh no, wrong place. Here, and it's probably just because the init functions aren't made to return bools. Not how they are designed. Oh, power up the device. That's an important step. Let's power up the device. Oh, I have the front panel open. Where's the temps? Try to make sure I get the temps. So we'll close that for now. So it looks like we configured the device. To finish this off, let's do a quick so set wire, set key, set wire in value, set wire. Let's open the OK Pi, and where is the wire? Wire. A good place that explains that. Let's look at the Opal Kelly API. Opal Kelly API documentation. Application API, which is Python. Activate trigger. Okay, let's see if they got release notes in here. Let's try to do this the official way instead of just they have notes here. That's not documentation, is it? Nope. So we go to documentation, HTML. Yeah, let's just so we're looking at the main page classes. We want the wire. Where is the spaces? Space members page. Oh, we're looking for the wires. Where would the wire? Opal Kelly classes. Devices. Okay, let's just see what does the function look like. Self XEM set wire. Where can okay. Transferring data. So it looks like you can just do multiple values. Okay, cool. We can do multiple values. So this is just a quick toggle. Do all these have? Okay, sure. So we're gonna say we want address 0 to be all. Oh, is that a mask? Maybe that's a mask. That makes sense. Where we did it. Let's find out if we did it. Let's load up the first. Does it work? Okay, that's up and going. So is there, oh, okay, update wires in. Okay, so address, mask, whatnot. I wish there was some documentation. There's a reconfiguration. Boom. Okay, so we're working. I assume that's a mask, right? So if I put like well, if I do this, is this like no mask? You just assume that it's maskless? You just assume it's maskless? How do we confirm it's a mask? Well, if we do like 0, if we do 3 0, and that's our mask, and we do FF, is this a mask or this? What's what this? Okay, yeah, that's a mask. Where do I find the documentation for that? Like, there should totally be documentation for that. Where do I find classes? What does this fall underneath? Because it's device info, right here. What's the, it's a front panel device. Front panel device. So this does all the devices. So this, that must be it. Where I'm not seeing driver, do licenses samples. Okay, we'll just call that as is. So that's the Python. Yay. Now, so that's working. That's nice. Back here. So we want to start the server right there. And each time the server gets a packet, right? Break, receive data. So let's do a counter here, right? Count counter equals 0. Map it up. Counter counter plus equals 1. Okay. Yeah, let's run it. You don't like that in my server? What are we doing here that's upsetting? Okay, start server. So it can't do the swig in a object. Okay, that's easy. Let's just not do it adjacent. We'll just straight up go into the server. Okay. I'm sorry, did you know it was your own server? We won't do it as a thing, it's okay. Um oh, Okay, so it's just going too fast. Counter. Shifted over by what? 24. Okay, it's too slow. Try 8. Over by 0. And last time this worked, right? It was all red. Weird. I want a counter based upon my packages. Why is it not setting them down? What is there something special for setting them down? Oh, it's a mask. Okay, it's a two-way mask. They did a two-way mask. So you have a mask to put things up, and you have a mask to put things down. So that is, I need documentation on this. Where do I find documentation on this? So we want zeros. So mask for zeros, so ones, and mask for zeros or ones to zeros. Okay. How did they do the counter then? Yeah. Okay, you can barely see the lights now. They're barely blinking. I don't think you actually see them on the video. What if we take this one out, right? What does that do? Does it just set them all to zeros? Let us not worry about the mask then. So this mask seems like an extra feature. Let's just not use it. There we go. Okay, so note, Did they explain? They don't. And I want some API references. These are the API registry. Describes a single register update. That's not what I want. Is there a search? From panel devices. We go. This is the constructor though. Get returns number available devices. Get serial. Nope. Or get device. Oh, here. Get. So what do we do here? We are up here. We are to do front panel devices open. What does open get us in the front panel devices? Open. So update wires in. Okay, set wire value. Here we go. Oh, the second one's the mask. It's EP value mask. I had it reversed. Okay, value and then mask. Cool, finally found the documentation. Thank you. Cool. So that's good. We have a counter. I want to go a little faster, so we're going to where is that? Oh, no, I want that 4. Let's do this as a 2. Okay, that's slow enough that I think we can just straight up go the default counter. Okay, so let's see. How do we get data from the device? Okay, let's read the documentation. We want to do a get wire out value. Okay, yeah, so we just get the value. First, we want to update wires out. So what we want in this situation, right? We want, it's gonna be self dot, self dot that, and right here, get wire. So it's gonna be self dot XEM dot. Is it lowercase? We'll keep it uppercase, something like this. Okay, let's go back to the first VHD. What is yeah, we're gonna do 2-0. That's the right one. 2-0. 2-0. Okay. There we go. We have everything set up. Now we just you may want to use a pipe or something for this, but we'll have to figure it out. Okay. Still shifting all zeros through our port, but we're getting closer. So let's just kind of going down here where we do the length. Do we do anything with the bits left? Bytes left. Yeah, we kind of just ignore it and just go by byte value, don't we? I think the empty TMS is just fine. Okay, so what we would want to do in this situation is we want to write this to a given location. Okay, so we'll say address 1 is now TMS. This doesn't really matter. It doesn't go anywhere. I think it doesn't go anywhere. Let's check the hardware real quick. This is using the first one. This is going to the math wire. So that's fine. Let me see. Can I do multiple? Wire in. No, we want to do set wire in value. So we can update both of them. So and let's just get rid of these obnoxious print statements all the time. To there, to there. But yeah, that's probably all we can do right now. Okay, we see the LEDs are moving, we're receiving data. Cool. Everything seems to be happy. Let's go ahead and turn the debug on so we can see what JTAG messages it's trying to do. So these are the JTAG things the virtual cable is trying to do. And we're going to have to figure out the best way to work it out. Let's go back to the API real quick. There was something interesting. Go back to programming languages. Let's go to the HDL real quick. Sure. What's trigger? Where are the trigger outs? Because we have these trigger. Okay, trigger in. I don't see OTA trigger out. So let's go figure out what those are. Wire in, wire out. Only so many of these, right? Address space. Oh, that's just how much. Trigger in, trigger out. Okay, trigger out. The target may trigger the host using the module. Contains 32 independent triggers, which are monitored with respect to EP clock. If disturbed for the rising edge, then the trigger will be set. The next time the host checks the trigger value, the trigger will be cleared. Okay, well, you can use the trigger ins and the trigger outs for data. I like that. Okay, so the next thing, I'll let this run in the background, and you can see the counters moving on the device. Let's look at here. So if we go to File, no, I'm wrong place. We go to Language Templates, right? We're going to type in JTAG. So under the Kintex UltraScale, because I don't think, or no, under the Kintex UltraScale Plus, because they haven't added Artix UltraScale Plus yet, they haven't added the Artix UltraScale Plus. That just makes things hard. Well, we'll assume Kintex UltraScale Plus. We're going to do VHDL because that's the right way. So we go here, we have a JTAG port access. Right here, master JTAG, boom, easy peasy. So what we need to do is set up the TDI, TC. Yeah, so the T clock, we can hook that up to the OK clock. This the OK library output a clock. I want a clock. Do you have a clock? So you have the OK clock. So OK clock is running 100 megahertz. We're gonna have to clock divide. We'll do it down to 50, 40. We'll have to clock divide. So if we go back to OK JTAG, this OK clock. Okay, so let's make some notes here. I don't think we'll get to it today. I only got like 10 more minutes, but let's make some notes. How to connect OK host to master JTAG. So let's add the port. Where'd the port go? Right here. Master JTAG instance. Close. Did I not copy thing? There we go. Close. We're gonna call this SLR0 JTAG. And zoom. Okay. So T clock should probably be 50 megahertz. 100 is a little. Okay, let's actually go look this up, right? UltraScale configuration guide. Let's look this up, right? We want to look at the JTAG speed. Where will you give me JTAG? There's going to be boundaries somewhere in here. I don't know. Hey, look it. Got the guy right here. This is our device. Is there megahertz? Internal C clock. This is less than. This is greater than. Okay, it's confident it can do 100 megahertz. Okay, right here. Okay. Okay. There's a lot of clocks. Okay, let's keep it 50. We're gonna clock divide it down. Okay, we're gonna do a clock divide to help us do the data. And we're just going to transfer all 32 bits each time. So we'll probably want to do a simple state machine. Right. It's going to have a idle, waits for trigger in. We should probably have some data out. We'll use a wire for data out. So then we're going to do the JTAG transfer. And then as we finish transfer, right? Finish transfer, we're going to trigger out and update wire out for TDI and status counter. See, ooh, how long do you think this will take, guys? I want to play around with it a little bit. Okay, so I guess that we'll do that next time, tomorrow, who knows? I think we hit our place right now where we're gonna do the VHDL portion of this next time. But we have the Python portion working. We have it connected here, so we have so you can see it fill the screen. And when you try to do targets, it's funny. Targets. DR shifted all the arrows. Okay. Yeah. Thanks for joining us. This project, when this will finish, we'll throw up an example on GitHub. We'll make do like an XEM example repository. So feel free to look this up online. Check it out. We'll be able to we'll demonstrate. Once we get it working, we'll demonstrate the Microblaze Debug Module. We'll demonstrate an ILA core, and we'll demonstrate the BBRAM to do that. Thank you for joining us. I am going to check on a few things, but hopefully I keep a schedule better, but